Let me just. Sounds good. Just want to see if I can see myself here. All right. Well, thank you so much, everyone, for coming today. So in August Talk, we'll have a very interesting topic that is higher compensation. So today's speaker, you can come here, so the camera can. Then you can stay in the camera. Okay. So our speaker is Yoon Jun Son. He was a grad student in the Mullins Group, but he recently graduated, so now he's Dr. Son. And Jun Jun has been doing a fantastic job in electrochemistry. He has explored different aspects of water electrolysis. And today he's going to give a short talk about ion compensation, which is a critical aspect for any electrochemist. So with that, I'd like to also thank all the people through Zoom and also watching this recording. Remember to follow us on social media so you can stay up to date with future seminars. And with that, I don't want to take too much of your time, and take it away.
Yeah. Thanks for a nice introduction, Raul, and thanks for attending this talk. Today I'm going to talk about the IR compensation, just touching the fundamental principle briefly, and want to move on to the how we can actually apply the IR compensation in practical experimental conditions. So, okay, before I start, I just want to ask, how many of you are familiar with three electrode system? Okay. How many of you have ever used IR compensation? Okay. Yeah, be good. Okay. Thanks for responding. Okay. So then the other people who didn't have any experience in three electrode system might be more familiar with the two electrode system. So two electrode system. Let me briefly explain the difference between the two electrode and three electrode system first. So most of the electrochemical device you can see in your daily life, like batteries, are based on the two electrode system like this. We have working anode or cathode when they are connected like this electrically, and we have ionically connected in the electrolyte. Okay. So when we do the electrochemical study for the two electrode system using only the anode and cathode, we can read the potential difference between the working and anode and cathode. But when we want to study the only one specific electrode, that's the time when we need to introduce this three electrode system. So for the three electrode system, literally we have three electrodes like this. One we call the working electrode, the other one is the common electrode, and third one is the reference electrode. So the difference is in the two electrode system, we only read the potential difference between two electrodes. So we cannot tell how much actual potential is being applied to the certain side of the electrode. So electrochemists wanted to apply actual potential to specific electrode and want to study the current response or resistance of that specific electrode, depending on the applied potential. So to do that, reference electrode is introduced, and when you apply the potential to the three electrode system, we are applying the potential versus this versus fixed potential of the reference electrode. So we can accurately apply the potential that we want. So that's the three electrode system. And there is one issue called IR potential drop. So when you immerse the reference electrode and apply potential, there is still some deviation between the actual potential that we want to apply, target potential that we want to apply, and actual potential that we want to apply to the working electrode. So it's coming because of the IR potential drop, which means literally just according to the Ohm's rule, V is equal to IR. There is a solution resistance between the working and reference electrode. So when you flow the current, there is a current times any series resistance between the working reference electrode, it will result in uh, potential drop, which is called IR potential drop. So if we really want to study the potential dependent behavior of the working electrode precisely, that's the when we need to conduct the IR compensation. So put them down here. So okay, that's so Renee. So actual potential applied to working electrode is the applied potential minus IR drop. So we want to make the applied potential to be same as the actual potential. So we intentionally do the IR compensation so that they can cancel out. And yeah, okay. So that's the IR potential drop, and we can do the IR compensation. So moving on, so this uncompensated resistance is mainly coming from the solution resistance between the working reference electrode. And yeah, that's the identity of the resistance, and we call it as uncompensated resistance. And for now, I'm going to call it RU, uncompensated resistance, because why does it? Why is it be called as the uncompensated resistance? Is of course, electrochemists wanted to minimize this RU value, but even though no matter how close they put the reference electrode close to the working electrode, and no matter uh, how high they increase the ionic conductivity of the solution, there's always exist some resistance. That's why it's called uncompensated resistance. So there are two most common methods to measure the uncompensated resistance. The first one is the impedance analysis, EIS, and the second one is the current interruption. Okay. Okay. So first, I want to ask, how many of you have ever used the impedance analysis? Okay, 5 of us. Okay. So impedance analysis is really useful in that we can decouple the impedance signal based on the frequency range. What it means is, so our electrochemical system, even though it's the chemical system, we have electro in front of the chemical, which means we can express our electrochemical system using some electrical component in the electrical circuit, like the electrical engineers do. So, uh, if I simply express most of the common electrochemical system, it would look like this. There is a resistor here coming from the solution resistance. And okay. So so what it means is something like this. When we have change that. We have working electrode and reference electrode. First, there is a solution resistance between reference and working electrode, and this resistance through the electrolyte exists in our electrochemical system. And additionally, there is a charge transfer resistance at the interface between our working electrode and electrolyte. So there is a charge transfer resistance, but at the same time, we have a electrochemical double layer between the at the interface between the working electrode and electrolyte. Right? So electrical double layers here. And this charge transfer reaction and double layer capacitance are put in the parallel because this, yep. So when the charge transfer resistance is smaller, when you flow the current, most of the current is going through the capacitor turn. And you can imagine when you flow the current through the capacitor, the charge will be accumulated in the double layer and it takes some time. So on the other hand, when we flow the current through the resistor, it doesn't require additional time, it just flows. So when you apply voltage, if the current flow through the resistors, we can get the current signal immediately. On the other hand, if the current flow through the capacitor, there is a time delay until we get the actual current signal. So impedance is based on this principle. So impedance is basically, instead of applying direct voltage, constant voltage, they're applying alternating voltage like this. They're applying alternating voltage. So when current flows through the resistance, current will also flow like this, right? Exactly the same phase. But when there is capacitor, there is a time delay because of this capacitor term. So current signal can appear a little later. Okay. So this is the okay. And so for the impedance analysis, we are interested in obtaining this RS value, solution resistance, series resistance, or we can also call uncompensated resistance between the working and reference electrode. So how we can obtain this uncompensated resistance of certain electrochemical system is doing impedance analysis, and this RC term, which is usually the electrochemical reaction of interest, has a frequency dependent signal, while this resistance doesn't have any frequency dependency. Frequency means how fast it responds to the voltage, the current. So when we really increase the frequency to the high range, this term, double layer capacitance cannot react to the frequency signal. So, and we can only obtain this series resistance. Does it make sense? Yep, go ahead.
So the RS will be equal to RU, like how to make.
Yes, here we can consider RU is same as RS. No, sorry about using two different terms.
So, sorry, could you please repeat once again? So we seek to obtain the uncompensated resistance, which is the resistor on the left, and then that's in series with two parallel circuit elements that are transferring double layer capacitance. So under what parameters does essentially that second circuit element, that's the combination of RCT and CAA, vanish, so that we just get this resistance?
Yes.
No, but like how? Like, sorry, could you repeat? Like under
what
conditions?
Yeah.
Is the only value you get the solution resistance?
Okay. So for impedance analysis, we scan the frequency range from, let's say, 1 hertz to 1 million hertz, 10 to the minus 6 hertz. And this RC circuit impedance signal, so we can get the impedance signal according to the frequency range, and we get the impedance signal. And so this RC circuit impedance signal shows up at the lower frequency region because, let's say, double layer charging, for example, always requires some time to respond to the applied voltage. So there is a phase shift occurs, which means there is an impedance term that exists. Here. Okay. This double layer term is mathematically can be expressed by, I'm a little confused. So it's inversely proportional to the frequency range. So when you increase the frequency, this term goes to zero. And that's why we can only obtain the resistance. But just conceptually, we can imagine if we apply voltage really fast, the charge accumulating in the double layer should be changing really fast. But if it is too fast, it cannot catch up with that AC voltage. So it looks like just staying like this. That's why these terms start to not show any frequency dependency anymore, even though it has the constant term. So So this term doesn't play a role, and we start to see the RS.
Yeah, that makes sense. I guess is it more so the term that you seek to eliminate, more importantly, the double layer capacitance term from confounding your results? Because it's like, by scanning a range of frequencies, you are able to deduce what that term is to be able to eliminate it. But when you eliminate the double layer capacitance term, does the charge transfer resistance term just sort of vanish with it?
Yeah.
Or do you, or is it just like, do you assume that the charge transfer resistance is just like, very low because it's usually just like a piece of metal or something that you're.
No, actually, I skip many explanations to make it simple. That's why, yeah. Yeah.
That like charge transfer resistance is kind of like coupled in with that capacitor because of how it's set up in the circuit.
Yeah.
So you just like apply that equation to fit that podium phase plot, and there's normally a very clear development, and so that resistor and capacitor just like fit that part, and the other resistor is like will fit the second resist development in the plot.
Yeah. Okay.
So it is pretty like separated in the plot when you.
Okay. Yeah. Go ahead.
Could you also have multiple RC elements to fit the curve, fit the microscope?
Multiple RC circuit.
Yeah.
It's possible depending on the electrochemical system. If we have multiple interfaces or multiple electrochemical process in series, we can add more RC circuit here additionally.
Yes. Okay, I know, I'm just asking because I work in batteries, so we typically have to use multiple.
You guys have, yeah.
Yeah. It's curious about
Yeah. 2 or 3 more RC circuit, right?
It could go up to like
Yeah.
Thanks.
Yeah. Just to briefly add a little bit more explanation, this R only has, so impedance is made up of the real number term resistance plus imaginary number term, something like this, reactance. So RCT contribute only the real number term. Capacitor can contribute to both of the term, and those two in parallel represent one impedance, and one impedance has their own frequency range. So these are coupled together. And so in short, using impedance analysis at really high frequency range, we can decouple the solution resistance or uncompensated resistance from the other factors. So impedance is really powerful that we can decouple the frequency dependence impedance signal in the electrochemical system. So yeah, even though we have more RC circuit, which means more electrochemical process, if they have different kinetics for each electrochemical process, we can decouple and obtain the charge transfer resistance or their double layer capacitance separately. And this single component just appear at really high frequencies, like 10 to the 5 hertz, which is 100 times or 1,000 times higher frequency range. So that's how we can obtain this series resistance or uncompensated resistance, and it's most commonly used to calculate the RU value. The other technique is might be less familiar with you guys, which is called current interruption. So while this one is using the AC technique, alternating voltage or alternating current, this is just based on DC, direct current technique. So let me briefly explain. So that time on the y-axis and tensor on the y-axis. So we are doing some electro analysis at certain potential in here, and out of sudden we interrupt the current and just set it as 0 and set the potential OCP immediately. Then potential will drop, and we can. So what it means is the same as this RC circuit here. So when we stop the current, potential drop immediately corresponding to the IR drop, because when potential changes to open circuit potential, there's no current flowing, which means there's no IR potential drop. So it immediately decreases this much. And then there is a very slow or linear decrease. So theoretically, there is a OCP. Theoretically, it should drop like this. If we change the potential should immediately change. But it only dropped this much and slowly decay to OCP. The reason for that is we have this RC circuit, which has a capacitor term here. As I said before, to put the charge in the double layer or to draw the charge from the double layer, it always takes some time. So the same thing is happening in this case. So for this resistor term, they always react immediately to the applied potential, and they immediately show the signal, like the current or potential drop. That's why it shows the immediate potential drop for this term. But for the RC circuit term, when you have a kind of big capacitance, it always takes a long time to reach open circuit potential. So it's slowly decay. So,
sorry, which vertical section refers to
this
IR?
Yeah. So y-axis is potential.
Yeah, but like which section of the drop is the IR compensate?
This linear steep drop, this much.
Okay, so prior to then the like exponential decay of the capacitor term.
Right.
That makes sense. Okay.
And I will call this one as the uncompensated voltage. So instead of measuring RU directly, we are measuring uncompensated voltage directly. And actual measurement is, they don't wait until we reach the OCP because it can take 5 minutes or something. So it takes too long. So it actually takes 1 millisecond, less than 1 millisecond. And they move on to the next potential that we want to apply. So, and then do the same thing. So they measure some potential data point in a few microseconds, a few tens of microseconds, and do the extrapolation like this. And just read the value here and believe that's the uncompensated voltage that we measure at certain potential. And this one can be used for the cyclic photometry or linear photometry during the analysis. Okay. Is there any question you might have?
So do you have to like fit all of these like individual data points?
The software do that fitting immediately in less than 1 millisecond. So they keep measuring the uncompensated voltage during the measurement, which means they keep measuring RU during the measurement. So the principle between the impedance and current interruption is quite different. This one is using the alternating current or alternating voltage, AC, while this one using the DC. And this one, we usually apply the impedance analysis before our actual electrochemical analysis. If we want to do the CB, we want to apply the accurate potential, then we need to obtain the uncompensated resistance first to do the IR compensation for the CB analysis. So that's when we do the impedance analysis first, obtain the RU value, and do the IR compensation for the actual electrochemical analysis like
So when
cyclophotometry.
you like plug that into your potentiostat, like it pops up with what your experiment is, and then there's at the bottom like uncompensated resistance, and you plug in
Yeah.
that specific value for that
Yes.
setup.
Yes.
Okay.
Yes, go ahead.
So is this when we do OCP, when we do OCP, what kind of OCP experiments? Like potential rate is equal to OCP experiment. Is it
Yes, it's the same principle. If any of you guys have ever done OCP decay analysis, when you change the potential to the open circuit potential is not changed to the constant value immediately. It always takes some time, 5 minutes, 10 minutes, depending on the material properties. This decay rate is different. So that's why we need some endurance for OCP analysis. So we are using that principle for the IR composition. So okay, I will move on to the actual IR composition method. So just to give an overview, first we need to measure the RU value, and then we gotta do the actual IR composition. So there are 3 different methods for the IR composition. What is IR compensation? One is called post IR compensation. It's a common language. Positive feedback. Third one is current infer. And for these, so remember, for RU measure, we have impedance and current interruption. Okay. So let me move on to the actual IR compensation method. There are 3 most common IR compensation methods being used in electrochemical analysis. So first one is the post IR computation, which means once we get the RU value, and we just do the electrochemical analysis without IR compensation. And after we get the whole electrochemical data, just we do the manual correction using our software. So as I said previously, actual tensor being applied to the electrode is going to be applied tensor minus higher potential drop. So for the post-IR compensation, we just get any electrochemical data, CV, without any IR compensation. And then we do the post-IR correction manually, just add the additional potential. So what happens is, if you're, then we go jump here. Let's say you have potential and current here, and you got the C3 signal like this, have redox fraction or some parallel direction like this, and you can do the manual post-IR correction in
Do study metal oxides?
yes, that's
You remember from
And it's like, oh, think about maybe this CV. It's like, okay.
yep. Then after post-IR correction, it looks like this. So just shifting the potential range as much as the higher potential drop. Does it make sense? So we have resistance value, and depending on the current, this value can be bigger. So this gap can get bigger. The low current in a small gap.
So if you have an Excel spreadsheet, you're gonna have like your voltage column,
Yeah.
your new voltage column you're about to make,
Yeah.
your current column.
Exactly.
It's gonna take like your E. So why are we adding it though? I'm just confused by the like.
Okay. For this case,
Yeah.
depending on the anodic or cathodic fraction. If this one is so when you apply, let's say, we want to apply the 1 voltage as actual voltage. So we apply the 1 voltage as our target, but there is a higher potential drop, let's say 0.2 voltage. So even though we wanted to apply the 1 voltage to the working electrode, it actually we apply the 0.8 voltage, right? So we cannot see the actual response, current response of the electrode corresponding to the 1 voltage. We are obtaining current corresponding to 0.8 voltage. So that's why we do the additional post-Hire fraction and then shift the potential region.
But wouldn't that be shifting it to the right though?
So maybe you guys must be confused about the sign or direction of the shifting, but it changed depending on whether it's the cathodic direction or anodic direction. Yeah, but it just moved to the direction requires less applied potential.
Yeah, basically closer to the origin.
Mm-hmm.
Yeah, or closer to the y-axis.
Mm-hmm. Moving close to the onset potential. Does it sense? Yeah, equilibrium potential. Yeah, become more ideal.
I have a question with just like, certain potentiostats, they have like the automatic IR compensation as a technique you can insert before like, I don't know, you like in your experiment, like I do that in my experiments. Like, do you do that in yours?
But we have that one too.
Yeah, but like, I don't know, like, does that introduce, like, have you, like, if you were to, for example, do like a manual IR compensation from a value that you deduced from, a series of, measurements that you made beforehand, and then compare that to just like doing the automatic IR compensation, do you get the same result?
That is really a good point. So theoretically, we can imagine their result should be same.
Yeah.
But in practice, we ended up getting totally different result depending on the electrochemical system. So for some electrochemical system, the automatic impedance IR compensation doesn't work well in the same way as the manual IR compensation. But in some cases, it doesn't work well. So I have slide for that one for the practical application part.
Okay.
And also here I can briefly explain. So automatic IR compensation.
I think it only does it at like one frequency, right?
Narrow frequency range.
Yeah.
So they anyway do the impedance analysis using the software really quick. So instead of we are actually conducting impedance analysis and get the whole impedance signal, the software itself just do the impedance analysis really quick and get the RU value at the really high frequency region.
Yeah.
And that's how it works. And then automatically use the positive feedback mode that I'm going to explain soon.
Okay.
Yeah.
That sounds good.
But there is a difference between doing actual manual impedance analysis and using automatic software, but it's kind of detailed. So I'll skip this time. So, okay. And this post-IR compensation, to do this one, we need to know the RU value, right? Okay. And let me briefly, okay. And moving on to positive feedback, we also need RU value. This one is just, let me briefly explain. It measured so during the once we put the RU value during the electrochemical analysis, it do the IR compensation during the electrochemical analysis in situ. So they have the current measure during the EC analysis, and they just multiply by RU and do the compensation during the analysis. So if we do the positive feedback analysis, theoretically, we're supposed to get this red electrochemical signal when we conduct the EC analysis. So from that point of view, the positive feedback mode is more convenient because we don't have to do the manual IR compensation. And third one, current error mode has benefit over these top two methods, because this one is basically coming from this current interruption RU measurement technique. Remember, we measured the VU value using the current interruption. And as I said, they measured the VU value in 10 microsecond or 1 millisecond. So they can keep measuring the RU value during the cycle glucometry. So if the RU value changes during the electrochemical testing, we can track how the RU value changes and immediately reflect that value. So for this current error mode, if we click this current error mode for the IR compensation using our software, we don't have to measure the RU before our analysis. It will automatically measure the RU during the analysis and do the IR compensation immediately. Okay. So to briefly summarize, these two methods, the post-IR compensation, we gotta get the RU value first before doing IR compensation, and positive feedback too. And current error mode, we don't need to get the RU value before the analysis. And these two, we use the constant RU value we obtain using impedance analysis. But this one, we can track how the RU value changes during the electrochemical testing. So this one has benefit from that point of view. But nevertheless, when you guys use IR computation, probably you will use the positive feedback mode, because this current mode has some limitation for practical applications, such as this cannot work well for the fast scan analysis. Let's say positive feedback mode can work at 1000 volts per sec, but this one has 10, 20, 100 millivolts per sec. So, and also this one requires really huge capacitor in the electrochemical system to obtain the accurate RU value. So there is some detailed pros and cons of each technique. Is there any question about RU measurement, IR compensation methods? Okay. Then, so part one is about the principle of IR compensation and meaning of RU. And second part is how we can actually apply this knowledge of IR compensation principle into practical condition and what kind of problem we can run into in the actual analysis. We'll switch to the slide. Can you hear me okay?
Yeah, I can. You can turn off.
Oh, that's one. Okay.
Yeah. No, yeah.
So,
So I think in the Zoom we're looking at the live. Okay. You were good.
okay, yeah, it should be better.
Yeah, there it is. There it is. Yeah.
So part two is how we can actually apply this IR computation and what kind of factor we need to consider practical application. So theoretically, this IR computation analysis can do the IR computation, and it should work very well, and we should be able to study the potential dependent behavior of the working electrode precisely by removing the IR potential drop. But in real experimental system, it's very complicated, as you guys already know. So there are some issues happening, and the meaning of uncompensated resistance can change. So overview of part two is performing accurate RU measurement and IR compensation is important. Otherwise, we might obtain the result something like this. So the black curve without IR compensation. So when we do the wrong IR compensation, we can see that this blue curve goes bend back and go backward. It doesn't make sense, right? When you apply one potential, we have two different current values. And so this is just one example how we can mess up the IR compensation and all the electrochemical analysis. So, but IR compensation in real experiments is really challenging because it is influenced by the characteristic of an electrochemical system. Like depending on what kind of electrochemical reaction we are interested in, like the battery reaction, redox reaction, or different electrocatalysis like water splitting reaction, CO2 reduction reaction. Depending on the characteristic of the electrochemical reaction, we have total different meaning of the RU. And also electro property can affect the R compensation and electrochemical testing condition like what potential is applied during the R compensation, what is the current or how long we operate the electrochemical testing condition can actually affect the RU value we measure and can interfere with the R compensation. So I'm going to briefly touch those examples. So our goal for practical IR compensation is we got to first understand what is the RU in specific electrochemical system. And there are 3 different IR compensation methods, but some of them does work for a certain system, the others might not work. So I'm going to show some example. So first example is the CO2 reduction reaction. So it's kind of popular electrocatalysis reaction. So depending on how we apply our compensation here, so in the x-axis, the left column is the no R compensation, and PF means positive feedback, CI means current inner mode, so different IR compensation method. And here, 60, 80%, okay, I forgot to mention this one. So we can apply different degree of IR compensation. So theoretically, we should apply the current times RU, and we gotta do the 100% IR compensation, right? That's how we can actually apply the wet potential. But for this most common technique, positive feedback mode, when we apply the 100%, we often run into the oscillation of the electrochemical signal, and it fails quite often. And that's why people usually do the 80 to 90% degree of IR compensation. So there's a gap between the ideal actually applied potential and practically achievable potential. So people use here 80% is given as the example. And depending on, so all these different types of IR compensation, 60% positive feedback, 80% positive feedback, current inner mode, 100% are all commonly used. But depending on how we perform the IR compensation here, we can obtain the different activity from the same catalytic electrode and even different selectivity of catalytic electrode. So in the CO2 reduction reaction, they produce lots of products. So it's important to have accurate information, what kind of chemical product we can obtain from this catalytic electrode. And usually the higher the carbon number here, C2H4 is more appreciated compared to carbon monoxide and CH4 or hydrogen. Hydrogen is the side reaction here. But even for the same electrode, depending on how we do the R compensation, we get the totally different activity and get the totally different selectivity. So this is just one example how R compensation, active R compensation is important. And another characteristic of the CO2 reduction system is as we run the electrochemical testing, the solution resistance does decrease. So that means RU value decrease. So IR compensation value should changes. But if we do the impedance analysis first before measuring the performance and do the positive feedback mode, we cannot reflect how the RU changes because we put the initial RU value, but we didn't know what RU value actually exists in the electrochemical system. In that case, we can totally mess up the RU compensation because we are using the wrong RU value, which is not true anymore after like 100 minutes. So this kind of issue can happen for the CO2 reduction system. So what can we do to avoid these issues? So one method is just doing impedance analysis for every certain cycle, every certain period of time, and obtain the RU value and do the IR compensation periodically, which sounds quite annoying. And second method is just using current interruption. So as I said before, current interruption method does measure the RU during the electrochemical analysis. So they can in situ track how RU value changes during the electrochemical analysis. So we can choose either current interruption mode or should conduct the impedance for every certain cycles. Okay, and also in the first part, I explained the uncompensated resistance is mainly coming from the solution resistance between the reference and working electrode. But depending on the electrode properties, we can have additional components. And maybe you guys can guess based on this scheme.
Okay, what's the question?
So in the first part, RU is just determined by the solution resistance between the working electrode and reference electrode. But depending on the electrode properties, we might have additional component of the RU in addition to solution resistance. Double layer, nice try. So double layer is actually filling the double layer and transfer electron through the double layer is the charge transfer resistance that is your main electric diffusion through the solution.
No, that's not right.
Maybe you can look at the orange line.
Oh, charge transfer.
Diffusion.
Diffusion through the electrode. Did you say? Was close. Was close. But ion transport is considered the mass transport. So the same. So yeah, right. So the yellow line is the charge transport, electron transport, or hole transport through the catalyst layer. So let me just show you. Yes.
We have will contain like several components.
Yep.
Yeah, but like usually, like you would like to hope that your uncompensated resistance is like mostly due to
Solution resistance. But yeah, that's true. That's what most electrochemists have believed for a long time. But it turns out, depending on the electric property, let's say you have a semiconducting material, you do the Moshaki analysis, so your electrode should be semiconducting, and your electrode has certain thickness, right? So there is always electron transfer resistance or hole transfer resistance through your electrode. So when you do measure the RU value using impedance or current interruption, you have solution resistance and electron transfer resistance together in the RU. It's kind of inevitable unless we use really metallic material and super thin, then we can ignore the electron transfer resistance through the electrode or any electrode. But battery material, electrocatalyst, and spool capacitor, many of them are based on the oxide or transient metal compound like sulfide, punictide. They all have some conductivity issues. So it's likely to have some electron transport resistance through the catalyst layer. Also, we often deposit or grow our catalyst or main electrode on the current collector or any substrate material. So there can exist additional contact resistance or contact impedance between the substrate, our catalyst layer, and also depending on how we clipped our electrode, we can have additional contact impedance between our clip, alligator clip, and our electrode. That's what this scheme shows. We have this gray dot contact impedance and electron transport resistance through the electrode. And for gas evolving catalytic electrode like the hydrogen evolution reaction, oxygen evolution reaction, their product is bubbles. And when bubble is produced, they are kind of staying near the electrode surface and they kind of hinder ionic transport. So they increase the solution resistance at the interface. So they can be also reflected in the RU measurement. So depending on the type of electrochemical reaction, whether they have gas evolving product or not, and depending on the electrode property, whether they are metallic, semiconducting, thick or thin, they can have different components of RU. So we need to understand this one for doing correct IR compensation. Yeah, Chika, go ahead.
Yes. Each one is in reaction which second and then we have the loose standards. Then the current interrupt will be best method majority RU.
Can you repeat your question?
So what I'm saying is that so in a situation when we have a low, we're using a low scan rate in our reaction and a low scan rate. So in any of our water splitting reactions, could it be that the current interrupt mode is the best method to measure the hazards?
Okay. It depends on your purpose. So if you want to do the IR compensation, including the bubble induced resistance, then current neuron mode can be beneficial.
I think that probably if I can add, the problem there is that which potential you mentioned in talking about. Because for instance, if you want to do positive feedback for LFE, you don't need to measure the uncompensated resistance at like high potentials where you have the open issue. So you can just do it close to the open potential. Of course, it depends if you have a non-conductive hydroxide oxide, you need to make sure the material is conductive. But you can do it at a low potential where you don't have open issue, so you can carefully get the RU value. But if, for instance, I think Yoon Jun mentioned the same thing when I was doing my class using the electrolytes. When you do impedance at a potential where you have a lot of bubbles, you will see these contribution from bubbles that so he's right. It depends on the application of your purpose.
So current neuron mode has it's gonna be pops up in the later slide. Okay, so let me move on quickly. Also, depending on the electromorphology, the identity of RU can change. So this is just a scheme for the compact electrode. We have substrate, compact catalyst layer. So when we measure the RU, we have the contact resistance, electron transfer resistance here, catalyst, and solution resistance. So RU meaning is same as the sum of these three resistance. But what happens if we do the RU measurement for the porous electrode? So we quite often use the porous electrode for battery or catalyst application. So instead of just measuring this, so as opposed to the compact electrode cases, we have this number one case, solution is actually touching the substrate. So this number one slot and number two, including the solution resistance plus electron transfer resistance plus contact resistance, they are existing in parallel. And usually catalyst has some conductivity issue. In that case, resistance through the number one cases has less resistance compared to the number two. It's kind of straightforward that number two, through this catalyst layer, we have multiple RU component, while number one has just single solution resistance. So the electrochemical system, when they flow the current, it bypass to the number one cases. So even though we have number one and two at the same time, when we do the RU measurement, we are just measuring the solution resistance through the number one cases. So this is something that many people miss when they do the RU compensation.
But like when you measure the uncompensated resistance, I mean, you're going to get only one value.
Mm-hmm.
So you're saying that one value is.
If it is compact electrode morphology, that one RU value that you obtain.
Yeah, it's a combination. But then like. Oh, I see. Like the porous catalyst sample is like, if you're saying it's like that huge like circuit element that's like a combination.
So one and two is existing in parallel.
It's like two things in.
Yeah. Tell.
Yeah.
Which one is true? For this, even though I show this equivalent circuit, you don't even have to do the fitting. The RU value you're going to get is going to be this solution resistance only, because when the current is flowing through this electrochemical system, it prefers to flow through the number one cases because it has lower resistance. Mm-hmm. Yes. So yes, but here the applying the R compensation is same. Just we obtain the RU value and do the R compensation. But the actual meaning of R compensation change depending on the morphology of the electrode. If we do the R compensation for the compact electrode, we did compensate electron transfer resistance and contact resistance, everything. So we get the higher activity or something. So if we do the R compensation, RU measurement in the porous electrode, we are only compensating the solution resistance. So our obtained electrochemical signal or electrochemical performance is still kind of restricted by the contact resistance and electron transfer resistance through the catalyst layer. Mm-hmm.
Hey, Jun, kind of question here. So does that mean that also, if, let's say that someone deposits a catalyst on the surface of the substrate, but they don't fully cover the substrate from one side, for instance, so does that mean that you need to definitely make sure that the substrate is completely coated with the catalyst and maybe with like plastic PMS or something on the other side? If not, you will get the wrong resistance value.
Yes, if your substrate is conductive, let's say nickel foil, front side you have oxide catalyst layer on the front side, back side is metallic nickel.
Right.
Yeah, you are mainly getting the RU through the solution resistance to the metallic part. Yep.
Is the I guess like another comparison between these two morphologies is the idea of like, for example, if you have like a series of catalytic materials that you're controlling, like the dope, like if you're doing like a metallic catalyst and you're controlling the percentage of your alloy, and you see an improvement in activity. If you're in the compact catalyst morphology, are you unable to like say, or could you be unable to say that you're like truly increasing the intrinsic activity of the catalyst, because you could possibly just be simply increasing the beat charge or decreasing the charge transfer resistance through the catalyst, so you'll get a faster current response, a better current response. Whereas the porous catalyst would be easier to argue that you are improving the intrinsic activity.
Okay.
Or is it more so that as long as you just do the iron compensation for both and just account for the uncompensated resistance like your
So very good point. And it depends on the purpose and depends on how you define the intrinsic activity. So I need to double check that one first. So when you say the intrinsic activity, that one is the intrinsic activity of the electrode that includes the meaning of the intrinsic catalytic activity of each active site plus electron transport through the catalyst layer.
So like, yeah, I guess if you were to, but like if you were reporting turnover frequency.
Turnover frequency.
Yeah,
for that point of view, oppositely, compact electrode is better, because if you are interested in turnover frequency, that means you're interested in the intrinsic catalytic activity per active site and see whether that bimetallic composition or doping does increase is helpful to lower the kinetic barrier, right, for that electrochemical reaction only, excluding any electron transport through the catalyst layer. In that case, if you do the R composition in the compact layer, you compensate all the electron transport resistance through the catalyst layer, then you can better study the intrinsic activity of the electrode, intrinsic catalytic activity of your bimetallic or doped material.
Yeah, that makes sense. I guess. So in other words, pretty much like your compact catalyst layer compared to the porous one is like you were able to, I guess, like more unambiguously do your IR compensation for it.
Or
less ambiguously to your IR compensation for compact morphology.
For both are so just ambiguous. I don't get them meaning, well, because this compact one always just includes all the series of the resistance. And first one only includes solution resistance. Is that what you mean when you say ambiguous? It is. Yeah.
This makes sense.
Yeah. Just each system reflect different RU components. Okay. Okay, so depending on the electromorphology, the meaning of the RU can change, even though we do the same analysis. Yeah. So it's good to know. Okay. And I want to just briefly touch the impact of contact impedance. So one of the components of the RU is the contact impedance between the substrate catalyst layer or substrate and electrode clip. And in that case, so theoretically, we are supposed to obtain just one semicircle from the Nyquist impedance analysis, which is coming from RU is the uncompensated resistance, and this one is coming from the RC circuit. But when you have a contact impedance means additional RC circuit. So we have additional semicircle here in the high frequency region. So instead of main semicircle for the electrochemical reaction of interest, we have additional semicircle here, and it's going to bother the accurate IR compensation. So when you have contact impedance, they usually pops up at really high frequency range, where we usually measure the RU value as a series resistance. So depending on how we measure the RU using impedance or current inner mode, this is just an example. I will skip the detailed explanation. So current inner mode can measure the RU value in the middle of here. And automatic IR compensation that Jay mentioned, it can measure the RU value at the really high frequency range here. And yeah, if we do the manual impedance analysis, we can decide to use the RU value here after this first semicircle to exclude the contact impedance in the RU. Okay. So when you have contact impedance, we can get several different RU values depending on our purpose, depending on our methods. So if we compare this green current inner mode and PF 100% positive feedback mode, both are using 100% IR compensation, but we can get the different OER catalytic activity here because of the different RU value we obtain depending on how we measure the RU. So this is kind of too detailed. I will just move on. So just keep in mind, depending on what kind of component you have in your electrode, it can affect the RU measurement, and it can result in different catalytic activity or any electrochemical performance. So in the literature, many people just doesn't differentiate different IR compensation method and just choose either of this one and report their OER activity or any catalytic activity. And I would say if they have contact impedance and they use the current inner mode, they can overestimate their OER activity. So some people argue they achieved the world's best performance using current inner mode, and that's the time I suspect their results. So, okay, they may do different IR compensation, and that's why they can beat other catalysts. So, it's always good to be careful about our IR compensation. And also, electrochemical testing condition can affect the RU value. So we have electron transport resistance. So for example, OER catalyst material like nickel hydroxide is insulating. But before the OER, we go through the anodic redox reaction and form the nickel oxyhydroxide. And nickel oxyhydroxide acts as the OER catalyst. But during that redox transformation, conductivity of the catalyst layer changes. Nickel hydroxide, super insulating. Nickel oxyhydroxide, okay conductive, semiconductive material. So it's actually detectable using potential dependent impedance analysis. So if you compare this 0.924 voltage and all the other more positive potential, this is the potential before and after that phase transformation from nickel hydroxide to oxyhydroxide, and we can actually see the RU value changes as we increase the potential because of the electron transport resistance through the catalyst layer did decrease as it formed more conductive nickel oxyhydroxide. So one lesson here is that depending on how we perform the RU measurement by changing the impedance analysis or applied potential, we can decouple the RU component. So just, yeah. Okay. And the other thing is bubble resistance. So electrochemical reaction like oxygen evolution reaction, we produce oxygen bubble and they can block the catalytic active site and increase the solution resistance at the interface. So this bubble resistance can change depending on time. So if we just measure the RU in the beginning of our experiment, RU value is pretty small, but as we increase the OER testing time and measure the RU continuously, we can see the RU value does increase because as bubble accumulate near the surface of the electrode, solution resistance increase and RU value changes. So this is the OER activity curve. So depending on the current region also. So when we have high operating current density for OER catalyst, which means we are producing lots of oxygen bubble, which means we can expect there is more oxygen accumulation and more bubble induced resistance. And I could actually observe that kind of increase. So at low operating current OER current density, RU value is 1.4, but as current density increased to 500 and 700 milliampere, it increased to 1.45 and 49. And this is the result. So because of bubble, we can see the more, So depending on how we perform our compensation, when we include the bubble resistance, we can achieve higher OER activity. So when you guys compare the performance of batteries, capacitor, catalytic electrode, we should note what kind of IR compensation method they use and what was the actual condition for that IR compensation. Depending on applied potential for RU measurement or operating current density, they can do totally different IR compensation and kind of overestimate or underestimate their performance. So just one example, and I will briefly show you. So IR compensation not just affect the catalytic activity measurement, it can also affect the redox peak analysis. I guess battery people might be more interested in this one because they do lots of analysis for the capacity measurement, pseudo-capacitance. So supercapacitor batteries always measure the redox peak and compare their total capacity. But depending on how we perform our compensation, the shape of the redox peak can change, which means their potential dependency, and when they interpolate to the electrode can change. The interpretation can change. And surprisingly, depending on how we perform our compensation, the actual pseudo-capacitance can change. So the bottom figure shows the kind of thick nanoporous nickel oxide. So, nickel hydroxide can be used as the supercapacitor and batteries too. And this nickel hydroxide has a unique property that charge can be trapped in the electrode during the cyclic photometry. So depending on the IR compensation, they go through the different charge trapping and ended up showing different pseudo-capacitance at the end. So this is just one good example how IR compensation can also affect the redox peak analysis. So just to sum up, IR compensation, this principle is super simple. Just measure the RU using either technique, impedance, or current element, and just do the IR compensation using one of the three methods. Very straightforward, but in reality, the complicated electrochemical system, like electrode properties and what kind of electrochemical condition that we use, it affect the meaning of the RU, its components. So we should keep in mind its impact and do the correct IR compensation. And this is all for today's talk, and I'm happy to take any question if you have. Questions?
Yeah, discussions. So, going to the
Is there also any questions from the chat? Okay, thank you. Go ahead. One question, Yoon Jun. So in trying to summarize everything here, let's say that I am someone who never tried higher compensation. So what do you think is the best strategy to start understanding what's the best technique that I should use for my material? Do you have any like recommendations or suggestions on what to do?
For your material.
Yeah, let's say that I don't know anything about air compensation. I just know that I can do post IR, positive feedback, current interruption.
Okay.
I have my sample. So what should I do?
So best and easiest way to understand the IR compensation is actually doing the manual impedance analysis and see where you get the series resistance, uncompensated resistance, and which frequency, and just try to apply the RU value using the positive feedback mode and change the degree of IR compensation and see how the performance changes. And if your material has unique characteristic like the material phase transformation during your depending on the potential, you can do the impedance analysis at different potential. Then you might see the RU value changes with the applied potential. Then you do the IR compensation using the new RU value and see how that affect your electrochemical analysis. So you might observe different catalytic activity or different pseudocapacitance of your materials. So it's good to start with the impedance analysis and positive feedback. And once you are sure that you understand your electrochemical system, specific electrochemical system, then you can jump onto the current error mode and post-IR compensation and see whether they show any difference or not. Then each electrochemical system have only a few options. Yeah. So yeah, there is no perfect solution for each system. So you gotta figure out by yourself by playing with your electrochemical system.
Okay, I guess I have another question. So you mentioned that the contact resistance is also important when you have like you may have like different contributions to the total uncompensated resistance. And I think that's a pretty common issue that sometimes we have because we use different kind of alligator clips or titanium clips, and also we use different substrates. I know that maybe the answer is it depends, but could you please just give a summary of what are the best and the worst substrates and also the best and worst clips? Like for instance, I know just an example. I know that titanium is good because it's not OER active, for instance. It's not a good catalyst. So a lot of people use titanium. But you can have titanium oxide and you may have issues because of titanium oxide. So could you please give us more examples?
I think you already answered those.
Okay,
Yeah, for sure.
most common,
So
right?
yeah, it's always better to go with the very conductive substrate material and inert material. Let's say for the titanium metal, even though it's conductive and widely used as the current collector for battery or right? Yeah, but titanium metal, even though it's cheap, conductive, it's easy to form the titanium, right? TiO2. So it can additionally develop the contact impedance between the catalyst layer and substrate.
Right.
And then you start to see the contact impedance impact on the target measurement and IR compensation. So it's always better to go with inert and superconducting material. So speaking of the alligator clip,
Right.
it's better to use the platinum clip is the best, or gold clip. Very conductive, doesn't form any oxide, but too expensive, right? Yeah. So the other option is titanium clip, or even though just normal alligator clip made of the stainless steel is fine as long as they have no surface oxide on it.
Right.
So the way I do is just do the sandpapering before I use, then you can see the RU value decrease. And also if you see the two semicircle because of the contact impedance formed by any oxide layer, you have, let's say, titanium metal, and if you have TiO2 layer between that, it's metal insulating metal layer, which means you have a capacitor layer, which means you have contact impedance coming from the resistor and capacitor. So you can remove the oxide layer, then you remove the contact impedance, and you can do the easy and accurate IR compensation. So yeah.
Electrode is one of them. So if your electrode is like a C connector, which is less
So you can go
conductive.
your okay.
Like if my alligator clips are like growing things and look like all gross, like that's bad.
Yeah,
Okay.
that's definitely bad. I have experience with using the rusted copper alligator clip. and you start to see very interesting impedance. Yeah. And
Fascinating.
the first semicircle will change with time.
Yeah.
Yeah. And change with your electrochemical condition.
Got it.
Mhm.
Cool. I'm glad I came.
Yeah.
And I guess that also, that means that we should be super careful about not touching the electrolyte with the lip, because that means that will also, as you mentioned, if you have like different metals or different surfaces exposed, basically the electrons will take the pathway without the
Right.
high resistance, right?
Yeah, right.
The smallest resistance.
Yeah, right. You're right. Yeah. So shouldn't touch your current collector or something or alligator clip to the electrolyte, and should be careful when you use some porous electrode like nickel foam.
Right.
There is a capillary effect. The electrolyte can go up to the current collector, and you got the different RU value.
Yeah, that's what you're seeing this. That's why you're seeing it, because I found that issue and I was like, what's going on? Why do I see like an extra synapse? Yeah.
Yeah. So IR composition is super straightforward principle, but we should take care of lots of experimental factors that can mess up our analysis.
We have a question from the chat from Anthony. Thank you, Yoon Jun. I'm working on a large size battery versus a small battery. Would I need to use different IR compensation techniques?
So I guess different size means different geometric area of the electrode, right? So theoretically, in that case, any type of IR compensation or RU measurement should work well theoretically, but practically, depending on if the size of the battery electrode is too big, there is a uneven electric potential applied to the current or your battery electrode. So you might get the different RU value, or even though you do obtain the right RU value, when you actually apply potential with the IR compensation, you're applying different IR compensation for each location, each local site. So that's the cons of using large battery electrode.
Right.
And also, if you use large size of battery electrode, you will see higher current, which means there are more IR potential drop. And given that positive feedback mode use not 100% IR compensation, they use usually 80 to 90%, which means you have a 10% of the error of the IR compensation. And when you use a bigger electrode, higher current, your IR potential error is going to be bigger. So if you want to study the electrode direction theoretically very accurately, it's better to use a small size of electrode. And you can use bigger electrode for the practical application in the coin cell or two electrode system. But if you want to study your electrode using three electrode system, it's always better to use small size of battery electrode.
Cool. All right. Is there any other question? No? No.
That's it.
Awesome. Yeah. Thank you so much, Yoon Jun. Sorry, sure.
Thank you for attending. It was wonderful. So appreciate it.
Yeah.
Hope you guys have a good.
Thanks so much, everyone, for watching this talk. We'll see you next time.